So that means we can measure the position with around 1 millimeter accurate. This is global accuracy. In a global reference frame, you need to use a reference frame which is the same everywhere on the Earth, so you can compare your results. The height I told you is a bit higher. That's normally it's a couple of millimeters. That's quite nice, you know. So and then you can see both the stations perform quite well. It depends also how good you can see the satellites. If you put GPS here outside the building and there's a big building next to it, it's blocking the satellite signal. So that's not ideal. You like to put on the roof so you can see the maximum of the horizon. Now getting back to this Phuket vertical motion of the island that you see here, and we updated the last paper, so this is running to 2022. So we're not running too far behind with publishing the data. This is the change of position in latitude, which is north, south. This is east-west, or longitude. This is vertical. Then you see the period where there was no earthquake. It looked linear, also here. Then you see the earthquake change the position horizontal a lot. I think here was together in the horizontal was 25 centimeters. And then you can see that after actually the position is changing, but the change is becoming less and less and less. Now, if you look at the vertical, we see that the island was slightly going up before the earthquake. And after the earthquake, after a couple months, we see that the island starts to go down, go down, go down. And then from here, we have our own station. And this is actually a combined of different data, different GPS stations. We could make this time series. So if you have the long period for more than 25 years, well, no, more, 27 years, that's where the powerful thing from GPS comes if you want to look at changes.
We are not expert or geoscientists, but this is normal trend or situation for before and after earthquake.
Yeah.
And if you monitor somewhere else, it will be something like this also, that going up a little bit after earthquake, the seismic, and then going down, same.
Yeah, but it will be scaled, so the effect will be less bigger or smaller depending on your distance to the earthquake. So if you go to Malaysia or you go to Bangkok, you will see similar, but it's smaller, you know, the effect. But the pattern is similar. This has been going on, this linear phase, maybe for a couple hundred years. We're just lucky or unlucky that the big earthquake happened in 2004. And then we see this change. But at some point, it will go back to this rate it had before the earthquake. But you see, right now, we are not there. We are still going in this direction. You still that this line and this line, or this line and this one are not the same. So we're still in the post-seismic. The land is still deforming. And the same here, you know, also here, the land is going down vertically. So at some point, it should be slowly going back to this rate. And then that's what we call a seismic cycle. It's repeated. But you are correct. So the pattern looks similar. Only the directions depend where the earthquake is. Here it's going down, but it could also go up, you know, and you would get a mirror pattern. But it's like we say. So for a long time, it's linear. Of course, if you never measured before and you start measure here, you will get completely wrong assumption about the long-term motion because you're in a different phase, you know. Fortunately, we measured before 2004. This is the same for the vertical. That's this solution, just a little bit different plot. Now we have the tide gauge and the satellite altimetry. Satellite altimetry says sea level rise. Oh, I have to go myself and look how much it is. 3-point-something millimeter per year. So that's absolute. It will not change because of the earthquake, because that's just how the satellite is looking to the oceans. So it doesn't care, unless there would be a big gravity change. That's gravity, but we cannot see this. The tide gauge actually, you see, is showing a change after this 2004. Suddenly the land is going up, the sea is going up quicker with respect to the land. Why? Because the land is going down suddenly, but before it was going up. So if the tide gauge says this, but in the beginning people didn't know, and they just fit the straight line from here to here. Now we know actually we have to differ between those different patterns before and after this. Okay, now we can if you measure something, you have to validate it, because otherwise people will not believe you. That's when you send in the paper as well. Now, fortunately, we have two ways to measure this relative sea level rise. One is with the old technique, the tide gauge, which is there. And the new one is using the satellite altimetry, the radar, to look at the sea. And we look at the vertical land motion from the GPS. If you subtract the vertical land motion from the absolute sea level rise, you get the relative sea level rise. If the sea is going up with 6 millimeters per year, the land is going up with 6 millimeters per year, you don't see any sea change. So we can validate that. And that's actually what you see here. It's two different techniques. One is the tide gauge, the other one is satellite data, GPS, and vertical land motion.
When we heard the publication of the news, they talk about increasing of the average sea level. So that is absolute or relative. So they don't subtract the change of the average land.
Normally, when they talk about global climate change and sea level rise, that's the absolute. So the relative can be higher, depending on what the coastline is doing. But it's just the sea itself is going. And actually, in this graph, you see where we. The other ones are the other combination. Well, you can subtract absolute sea level rise. You can also subtract. You can also combine with the tide gauge, and then you will get vertical line motion. So you can validate that using two different techniques. Now, just look at this one. You see that the black line, that's the salt minus vertical line motion. So that's the satellite, GPS, and radar altimetry. That's the black line. The green one is the tide gauge. Now, it's not perfect. There is some difference going here, but in general, it matches. So now we have two independent techniques which show the same result. So then, yeah, we validate. So it's quite important. Then we also looked at if we could see the same kind of pattern in different tide gauges in the south of Thailand. This is all Andaman Sea. Unfortunately, not always the tide gauge data is good. Sometimes the tide gauge station break down. Sometimes the pier get destroyed, or they change the reference point, and there is a difference in the vertical point. So it's not always perfect, but still we can try with. So we asked the data. Actually, you see for two stations, it's quite clear. Ranong station. I think the other one is Antrang. That's on the also on the Andaman Sea. They show a very similar pattern as the one station in Phuket. Actually, this one also in. I think Buraburi, this one, but then there is no data anymore, so we cannot see it. And then there's two which don't show. This one shows a little bit, but this one actually shows that the sea is going down. So something strange with the tide gauge. We don't know, or the point is not fixed, and the sediment is pushing to the pier or something, and then there's a vertical motion. So, but in general, we get agreement also at different. We have not looked at the Gulf of Thailand at this point. Now, if you have the two stations, the one I showed you on the bedrock and the one on the tide gauge, we can also look at the baseline to see if the platform is stable. So you just take the position from the one station and the position from the other station, you subtract from each other, so you get the absolute distance or 3D distance. Now, you can calculate the average for 1 month, and then you're just going to check if anything changed to that distance. Then, if nothing changed, the 2 points are not moving with respect to each other, so they should be stable. We know the 1 point is on bedrock, we're sure it's stable. This platform, we're not sure if it's stable, because in the past actually it was destroyed by a fisher boat, but then they built a new one. But if you look at this baseline, the distance is 4 kilometers between the two stations. Now, if you look at the horizontal, it's a flat line, which means there's nothing going on, so that's good. And also vertically, actually, if you look on the long term, you see there is some seasonal variation we call. I just upset the graph, but you see that again, the vertical component of the distance between the two stations seems to be stable. And actually, we have some idea why we see this. This has to do with the warming up of this platform, which is partly steel and concrete, and the other station is on bedrock. And this station is in the sea, which has a temperature. So I think it's related to different temperatures at the one station. And actually, it's not interesting at all. But from an engineering point of view, it's nice that we can see. It's not good to see, but you can see a little bit that there's a seasonal variation. And then that's the last slide to the first presentation. I think then there's another thing which is nice nowadays, which we can use, and it's actually very easy to master. If you have the GNSS data, you can also use the reflections, meaning the satellite signal from the satellite, is sometimes bouncing on the sea or on the land or a structure, and then it's hitting the antenna. We call this multipath. We don't want this data for positioning because it's wrong. The antenna should only measure the direct signal from the satellite. But if the high tide is here and the low tide is here, the signal is reflecting here on the sea, and at low tide it's reflecting down there. This is very nice. Actually, we can see it in the GPS data.
How do we know whether the signal is from reflection or the direct signal? How do we know it's direct signal from the satellite or reflection?
Because the reflected signal, because of the reflection, you lose energy. So the reflected signal arrives with a lower power or a decibel signal to noise ratio. Actually, that data we don't use in the positioning for the GPS because we call it bad data. It's at the side of the data spectrum. You know, you have the data with high signal to ratio. This is direct signal for sure. And then on the sides, you have this lower signal to noise ratio. That's mostly the poor data, which actually we throw out because we select a certain signal to noise. But for this application, you only want to have that data. So, but there's two things. You cannot see in the antenna where it comes from. So the way the processing is done is actually, it's quite smart, and the software, we didn't do it, but the software is also, it's freely available. You look at the possible reflections. That means you know where the satellites are flying above Earth. So you know at different elevation, a signal could come in low, and reflect and go back. And then if it's nearby, then it already comes in a steeper angle and it reflects, and then the satellite. So these are those directions you can see first. This is for the station PMBC. You can just run this program. It's online on the website. This is the possible reflections. So you already know you don't want to have reflections from the land. You get two. So those you exclude, you know. So, but here it's all sea. So you say, yeah, we can use this direction. So if we know that signal can be reflected by that satellite, we look in the data. If we see the low quality or the low signal to signal and the low decibel signal to noise level of signature of that satellite in the data. If we know the reflection is coming from that direction. We can also know purely from the geometrical where the satellite is. You don't need very precise orbits of the satellite. We know where the reflection comes from. So we can, and then we have to validate if that signal is a possible reflector. If we know where it comes from, we already know what height it ended up in, if it reflected lower because of geometry. So you have to collect all those points. A tide gauge will just sample 1 per 10 minutes, 1 per hour. Here it depends when we have the reflection. So you get like this pattern, but you can clearly already see that it's working because you can see that actually this is days. So you have the daily tide variation. And then you have the monthly tide with the moon. So you have the very high tide and the low tide variation, and it works. So here again, it's shown. So the software is actually not so complicated. You don't do processing for the position. You just look if you can see the bad quality signal and it coming from the direction you expect, and then you do. And there's some other quality checking, and then you can build. And then if you do it for a whole year or longer, you can actually also use it to monitor relative sea level rise. So it's actually a tide gauge, a free tide gauge in your GPS antenna. But you have to put your station near the sea where it can also see the seawater and not only the horizon. So that's the only thing. You have to find a good location, you know. A pier sometimes works, if not a boat parking in front of the GPS antenna. And this is something now we are also with DMR. We're gonna compare the measurements from GPS and from the reflection with the tide gauge from DMR nearby, and another tide gauge which you see where the other station, to see how good these techniques work. You know, so it's an easy way to monitoring. You can also have a dam, if you have a dam, like in Thailand, you have the dam to generate the electricity. So if you just put the GPS antenna on the dam, it will also receive the reflection from the water behind the dam. So you can monitor the height of the dam with the GPS like that. It works quite well. The precision is a couple centimeters, but for long term, the level go up sometimes meters, you know, with the dam at the dry or high season, with the wet or dry season. So that's also a nice thing. This is quite easy to do. You can learn this in half a day, how to run the software. So maybe in the future I can show you. Okay, that's the first, that's the last one. Yeah, that was my last presentation that was my last slide from the first one. Otherwise we fall asleep.
We need to take a break.
Yeah, we need to take a break. So I'll give you the copy, don't worry, I'll give you the copy of both of the presentations.
5 minutes or what? 10 นาทีเนาะ break. Okay. Maybe get some snack.
Now, the next one will be a little bit more technical on how to look at the time series, but still not in the sense that you have to be expert,
Okay.
but a little bit more.
I mean, you prepare these 2 slides, right? I mean, this one, the first, and the second one. That
Yeah.
I think maybe
Some of
half day we can finish, and but mainly we may talk to you about the project or the idea. I think you work with John Gordon and Gnss. About the Bangkok. But in the south, not yet project.
No, we don't really have. I mean, they already. We not actively have a project together now. You know, I mean, we have still with Macquarie because we still continue. Although the funding is finished, but we still have the cooperation. DMR will start off, but it's not active. So we have the potential, we have the interest, but we still have to materialize the real cooperation. So we work together, and you do something, your team do something, I do something. We sit together, or even
We need you.
public. Yeah, well, but I can also get you in touch with other people. I don't know everything.
We know the people. Let's say in Thailand previously, the research money is distributed directly to each university. your handy drive เดี๋ยวค่อยก๊อปตอนเริ่มเสร็จมาสองชุดไงสองชุด
เช่นนะดูเดี๋ยวนะ
แล้วเขาจองไว้แล้วจองไว้แล้วที่เปลี่ยนร้าน
ยายนะร้านไหนนะ
ป่ายางเดี๋ยวแปลสั่งใหม่ก็ได้เป็นจานไม่เดี๋ยวแปลสั่งใหม่เป็นจานก็ได้แยกออกมาก็ได้
แล้วได้มีใครไปบ้างเนี่ย
เดี๋ยวเราน่าจะไปได้แหละเช็คที่ว่า
ไปเพื่ออะไร
โอเคพิมพ์ Part 2 Episode 2
Where are my red dots, bro? I lose my red dots. I'm stupid here.
แต่อย่างดีนะไม่มีกลิ่นเล็ดรอดอันนี้เขาเปลี่ยนเป็น
All right. So this is part 2. This is more, a little bit more technical on how to obtain and interpret GNS research results. Before I just show you the time series. Now I'm going to try a little bit more. To do it real good, we should have more time and do some training together. And I give you some exercise and you can do yourself. And then we interact. But this is the first step. And as an example, I'm using vertical line motion. This is actually quite recent work. The paper just got accepted 2 days ago. And we have one of the co-authors in the room. But more on the formatting.
เที่ยงนี้ยิ่งเลี้ยง
That's the thing about networking, you know. So I mostly have many authors from many different groups, and it's nice because it's multidisciplinary work. And yeah, mostly I have many authors. Some people like to be the only author. I don't care. I like to have many authors.
You treat up lunch for celebration.
Yeah. Now, actually, you will explain the presentation for me. And I can go have a break. Okay, so it's so we looked at Malaysia data from the longest period we can look at from GPS point of view. The first measurements in Malaysia started from 1994. Only 2 points, but from this big geodesia European project to study tectonic motion. So and then later on they actually put their own station on the same point or nearby, continuous station which measured every day, and now we can collect all that data. So we have a very long period of data. We do focus on vertical line motion. So what you see here as example is just a vertical component of the GPS position solution. These are actually, I didn't tell you, these are weekly solutions. I average per week. If I would put day, it would be much more noisy. We use the weekly average. I mean, you also sample your biological samples. You also sometimes do 10 measurements and then you average them and then the noise level becomes low. So these are weekly. So yeah, and actually some of the data is near Songkla, as you will see, because Malaysia is not that far. Next. Yeah, this is the whole contents. Don't be afraid that it's a lot, but we'll get through it. It's about the same amount of slides. Briefly, this define vertical line motion. I think you know already. A little bit. I don't know if this one is still in because I already talked to you in the last one. And how we determine it with the GNSS. A little bit about the software we use, but that's just one slide. How we do the processing, but I'm mostly here we're gonna go into the results from Malaysia and see at those time series what interesting and how we can interpret the results. And actually, the aim of this work was to come up with relative sea level rise estimates for actually not only Peninsular but also East Malaysia, which is the Borneo part, the 2 states there. But for this presentation, I just took the part of the Malaysian peninsula, which is situated straight below Thailand. So vertical line motion It's defined as the absolute vertical motion of a landmass. And landmass is going to be the rock, well, a landmass in general, and either it's rock, which means it can only move up or down due to tectonic, or your point, GPS point, is on sediment layer, and then you're measuring the combined effect from tectonic plus subsidence. And because mostly people only make things subside, no mountain is going up due to human because it would take too much, or you have to pump a lot of water into the. That's actually also a countermeasure. Right? If you pump groundwater, you can also pump something back, or like CO2, you know, to balance for the future. You know, at least you could do like that. So the sources from vertical land motion, they are crustal deformation of the plate boundary. A tectonic plate is actually floating on the, it's not fluid, but you know, lava, you know, hot material. So the interior of the earth, even nowadays, after 4.5 billion years, if you believe, unless you believe in God and you think it's 6,000 years, but it's 4.5 billion. So the interior of the earth nowadays is still fluid, but hot, very fluid. So the plates are floating on that. So a tectonic plate cannot have a vertical motion because the lava is not flowing out. So in general, they're floating. So we only have horizontal motion. The plates are very big, so they are curved because the earth is curved, but they are only moving. They are floating, like you put some milk or on top of your coffee. So it's only horizontal, but not when the plates come together. Yeah? Where you have earthquakes, or they push together, or you get the Himalaya because they push together, or they pull apart, you get a deep ocean, you know, going on. So the plate can deform at the boundary. So where the two plates interact, there the plate can deform. So it's not the motion of the plate, it's the deformation. Same, you take a piece of paper, or I take this box. This box is only going to move horizontal, but if there's pressure on there, well, you see already. So it's deforming, you know. So this you can have. Those plate boundary regions can be very big. Thailand is in the plate boundary region of the Sumatra, of the Indian and the Australian plate, and then we call Sundaland. We call Southeast Asia is mostly on. So that's 600-700, even Bangkok 1,000 kilometers away. The land is still deforming due to this. Convergence, and the 9.2 earthquake is just this sudden release, you know, of this motion. So that's something important. So it's not immediately dangerous for Thailand, but the whole Thailand is deforming due to this location in the plate boundary zone. And the other one I told you already before is the human-induced land subsidence, or basically just groundwater extraction. And then there are also some seasonal changes, you know, due to atmospheric, oceanic, and hydrological loading. So you have the atmosphere, you have low and high pressure. So that means more gas or more air on the plate. So you compress a little bit the plate. So that's seasonal. The seasonal is not really a big issue. We're more interested in the long-term changes. And then we of course have, like you saw in the previous presentation, you have those genetic techniques. You know? And for this work, I'm only going to talk a little bit in this presentation about the GPS, but we use the data from the Malaysian active GPS or Gnss network. Thailand now also already has, since 2019, RTSD has the course or continuous operating reference network, and the Department of Land, I think they also have more. So Thailand also have those. But Malaysia already happened for a long time. 1999, they start already with their own. So we include that data. Apart from that, of course, as for Phuket, we also have looked at the satellite altimetry data minus the tide gauge. That's actually the validation way to look at vertical land motion. Vertical land motion can get direct from GPS or GNSS. Sorry, I always say GPS. Nowadays, we have to be politically correct and say GNSS. And another way to get this vertical land motion is looking at the difference between the satellite altimetry, absolute sea level rise, minus, in this case, the tide gauge, which is measuring relative sea level rise, if you subtract those, you end up with the vertical line motion. Theoretically, if the tide gauge data is correct, and if nothing strange has been going on. Okay, this one you can read later in detail. It's again now. Well, I put Phuket in the previous presentation. This is the same graph, but now for this work, it's the same situation. Peninsula Malaysia, which is located below Thailand, and then this is the Indian plate going below this whole area we call Sundaland. Then there is a phase when there's no earthquake happening, or no motion is zero. But then at some point the plate friction and pushing together is deforming. So some areas go down, some areas go up. And then there is the earthquake itself, which changed also the high position. But then there is a period of many years where still now the other way around, the point is going up or the island or is going down. So this would be for Phuket area, and some Malaysian stations should show the same because they are close to Phuket or relative to where the earthquake happened. So those three phases I talked to you in the previous talk, so I don't want to repeat them, but it's again an interseismic phase. That's before the earthquake, the post-seismic during, and the post-seismic after. Just remember those, and you'll be fine. Now, if you want to measure vertical land motion using Gnss, whatever application, reference point for sediment study, you can name it as you want, or to measure or look at the dam stability of the water dam or how it deforms with the water level behind the water dam. You need to have stable monuments on bedrock or sufficiently deep foundation depths of sediment layer. So then you have the concrete going down, or you see with the highway, they put the big pillars, bang, put them down. So you have a stable, because you don't want the antenna to just slide, you know. If you only put 1 meter and it rains and the soil gets wet, then the monument will slide. You don't want to measure that for your scientific research.
Like this building can.
This building has a strong foundation, so you can probably put the antenna. We often do that because the advantage of that is that you have a good visibility of the sky. Because if you put down in the field, then the building will block the sunlight. Okay, if you do this, is more technical, but if you do this observation, you clearly have to document them. If it's not continuous, but even continuous, you have to say what kind of antenna you're using, because different antenna have different height reference points. So we call this log sheet. So you have to document very nicely over many years. The data itself, actually from the receivers they give, we call it Gnss. It's an ASCII file. So there are all numbers in there. Typically, we only sample every 30 seconds. That's enough for this kind of study. But actually, we also can do 1 second, 1 hertz, or even higher. And this is useful for earthquakes, because then you even can use the GPS data as a seismological station. The GPS will measure the vibration, you know, due to the earthquake. But then,
Gnss is the name of software.
yeah, no, Gnss is the standard exchange format, because all the receivers use a binary format, but the binary format is not useful. So the Gnss is an ASCII file, and it just tells you per epoch at what time, how many satellites are tracked by the receiver, and then it gives you the measurements. One is the measurement we call the pseudo range, it's the code which is the satellite is transmitting, and the other one is for the scientific review, the wavelengths. Those wavelengths help. Without the wavelengths, we cannot get the millimeter. You know? So they're just numbers, and they're just increasing, and they're just per 30 seconds in the file. But it's the same. Every receiver you can convert to this format, and this is the preferred input format if you want to do processing yourself. If you have a station for a long period of time, you don't want to touch it. That means change the antenna, or if it's on a tripod, it's not stable. It should be all firm for many years and not change, because then you corrupt or your data will become not useful, you know. Okay, this is also technical. Now, in the past, we actually didn't use the data to the horizon, so 0 degree elevation, because then the signal has to pass a long way through the atmosphere, which gives a disturbance, and that actually reduces the quality of the position. But nowadays, we set always to 0, even in the processing, we still use 7 degrees. But maybe in 10 years, there will be better models to model the troposphere or delay. And now you can go back, research your old data, and do a better job because you already included all the data. So we not use all the data. And also this reflection data, you also have to put to 0, because the reflection data is actually coming in minus, but the antenna doesn't know. It just sees it as a 0, around 0 elevation, that data coming in. Yeah, and don't change your location from this building to the next building because they want to put something here, so you have to move there. And then 2 years after, you have to move there. That's not good for the science too. Preferably, you want to keep the station for many years. Now, the research methodology, but I think it's very similar to when you write a paper or you want to study something. The most important thing, of course, first is you have to define your research question. What are we going to look at? Just for example, I think for you, or might be interesting, for example, study the coastal erosion or the impact, So if we have that, of course, the next phase, also if you write a proposal, is to see what's already been done, either internationally or in Thailand, and make your research plan. If we know that, then then we're going to look if the GNSS data is important for that, what data is needed, and where can we get it from. Some data you can measure yourself, you can set up a station, but there are also stations from other groups, the government or from the Royal Council. You can get the data, you can apply for the data, so you don't have to measure yourself. Now, to get reliable scientific result, I just summarize like this. The first thing, which is always a very good thing, and that's also what we do when we do the hands-on training, that you first see if you can duplicate or re-engineer because normally when a paper is written, nowadays also it's open access and we even share the data. So you can normally get all the data which the original authors used also to do the work. Then first we need to make sure you can reproduce, duplicate or reproduce, meaning the same, those results, because then you know you're doing a good job. If you do that, then you can do your own job, of course. Get your own data, or get your data either from the public source. There are servers which provide you. I'm sure there's a core station from RTSD near Hachai or Songkla, that station we could use as a reference. Now we could maybe measure more points ourselves. So that's we have to do through the cooperation, and we have cooperation. Say, oh, we want the data from Phuket. I say, yeah, we have the station. Well, we already share. You can get, and maybe you want to have your own data. Then, of course, you need budget to measure that data in advance. This one, I don't want to go into detail. Compute the GPS position. One important thing is if you process data, it always gives you a position in X, Y, Z, the computer. That's a Cartesian coordinate reference frame. It's very simple. It's X, Z, X, Y, and then the 0 is at the center of the Earth. And then you have the digits which gives you the position either on land or if you would be in a plane. X, Y, Z is nice, but it's not useful for us to study any changes. That's why the local reference frame, northeast, north-south or latitude, east-west or longitude or vertical, is more logical to study because X, Y, Z can be anything depending where you are on the Earth. So that's why we convert. Most of the software will also give you automatically convert the position in degrees, latitude, longitude, semi-or That's the preferred format to work with. And although you have computed your positions, you'll have to look at them. Some of them might not good for various reasons, because the receiver was not working proper for a period, or somebody or a tree fell down near the antenna and blocked, So you also have to inspect the time series over a long period of time to see for outliers and remove them. So that's more technical work. Then this is more a bit the math, trend estimation. You also do that for samples. But for our, we talk about motion, millimeter per year, if you can trend them. You can do in some cases, it's also the signal or the motion is non-linear, so you need so that's all maths, but you have many software. Excel is the easiest example, but there's also other packages which can help you with that. Then the important thing always is to validate, verify results. And because if you say, yeah, some cloud is subsiding by 3 centimeters per year, but you made an error and it's only 3 millimeters per year, then the next time you're going to apply for a budget, you might not get your funding. So always, but that's also always good if you cooperate, you know. We also share our results with other people to double check and see if it's really makes sense, you know, apart from it's correct. And then that's the nice thing combined with the other techniques. So it can be non-genetic. You have some people studying the mangrove reduction, you know, and they have a long data set from that going back. Now we're going to look at the vertical land motion and sea level rise, and maybe you want to see if there's a correlation between those two. So that's why it's nice also to work with the people who study the shallow or PMBC, looking at the shallow water coral reef, how it goes. So there's a link with that. And interpretation, of course, is always an important thing. In this case, it is combined. Then the last thing, of course, is to publish the article. Mostly preferred nowadays or necessary is a multidisciplinary, where you have different experts joining in and that both maximizes your result, but just using a signal technique nowadays, it's not so, well, depends on the discipline, but in general, you can do more if you combine the different disciplines. And it can be genetic, what we do, but together with some people studying biology or even fish, retreating because of the warm water, and then you have the satellite temperature, and then you can work together on that, you know, so that's also nice. So, and of course, a nice article is nice both for yourself, for your career, but also for, for the general knowledge, and other scientists can learn about what you're doing and maybe improve or continue or combine in their own work. Okay, the software we use is, there's quite some packages for the scientific application. I just want to mention, and we have used different ones, but we are using the software for many years already from GPL. For universities, the license is free. You just have to apply for it. There's a quite difference in the type, because how you combine the measurements, the raw measurements, and zero difference. Without going too much detail, it just means that you can solve one station anywhere on the globe very accurately. If you have the double difference packages, they look at the baseline in between. So you have always the baseline still in your network, which theoretically can give you as good result, but it might be a little bit more tricky. And if you have one bad station in there, then it affects the baseline to the other station, and it can degrade the quality of your solution. So if you go for zero difference, you make your life easier. The GPX does everything for you up to the point you get those daily positions, and then it's up to you to combine them in a week position or build a time series over a long period of time. We also have ourselves through the years, and again, this we shared when we worked together. We did some scripts, we call it, because we mostly use Gypsy's running on Linux. It's not really on Windows. I mean, Gnss is working, they have a Windows version, but Windows always likes to crash after a while. The Linux server can run for years without need to reboot. No blue screen. So we have scripting to make life easier. Those can be shared. So at the end, you can even run this quite easily after a couple-day training course, which we hopefully, when my Malaysian colleague who lives nearby, we did it at Macquarie in the past, but we can do it again. So you can run it as a black box, and we can ensure that you get the good position, the same as we do. But of course, it's good to have a little bit more knowledge about the data, so you can check if something goes wrong. And you can also do it automatic. If you have your station up here, we can set it down that it does everything automatic. Even put to a web page, and every day there will be a new position, going. So all this we can set up. Important is the reference frame, but you don't have to worry about that. All your measurements should be in the same reference frame. Also for exchange with other groups if you want to compare. So, but that's also handled by the software. Yeah, and now we use it, of course, for a long time already in all those projects. We did work in Indonesia, Thailand. We have our own course also in Indonesia, and even also campaigns, which means we have many points. We cannot put the core station, it's too expensive, and also to maintain it. So we check every year, or when there's an earthquake, we check all those points as well. Okay, this is a little bit more why the zero differences is better, which is the Gypsy. There's other packages as well doing it, but GPL was the first one to introduce that one. I'm not going to read all of them, that's it, but it's faster and easier to get accurate absolute coordinates in ITRF. Okay, so and then there's a couple other points, you know, but you can read through them if you want later on if you're interested in this more specifically. So I always advise people to use zero difference package, and then it doesn't have to be Gypsy. Actually, the Chinese also have one. It's called Panda, but it's a clone, I think, of GPL. So, but there's more packages. But you should go for this kind of technique to make your life easy. Also, during an earthquake, if you have double difference, you're calculating the baseline change. If both the stations are moving from the earthquake or move differently, you don't know what the baseline change comes from this station or that station, because you have to use both at the same time. With zero difference, you just saw first this station doing this and this station separately. So you know very well the motion of both of them. So that's also nice. But and also in the future now, the products you need to have accurate position of the satellite to do this, but you also get, that's all include free. You don't have to pay anything for that. Nowadays, also Galileo is in there. But we can also use the Galileo data, which even should make our daily solution better, or the noise level go down.
That's only Galileo and GPS, right?
Yeah, they also have.
How about Baidu or Q-based, something like that, for Japanese or Chinese satellite?
Well, yeah, for the scientific, you need to have reliable products, and if you want the data over a long time, you have to have agencies to provide it. You know, I'm sure they exist, but in the past, the systems that were used internationally were GPS, GLONASS. GLONASS also they still make a product before. Baidu, they're also working on it, but the problem is that the Chinese government doesn't give all the details always on the antenna reference frame. They might do later. So the Baidu system is also a good system, but for scientific research, there might still be some information that's not available to get good operational products. So although it's good to switch on Baidu in your receiver, if you have the option to collect the data, you can collect GLONASS. For the scientific global community, I think right now it's still the best results are achieved with GPS only or GPS Galileo. But Baidu is okay. Maybe the Chinese have products for that as well.
Or Japanese?
The Japanese system, I mean, the Japanese have for sure. But GPL right now, they are mostly focused, because you can check in the IGS, it is global organization. What I know, I think the project before were Galileo GPS, but I'm sure they work on, but I don't know about the quality of those projects. If the reference orbit of the satellite of the Baidu at this moment cannot be so accurate as for the GPS from Galileo, it's not worthwhile to include the Baidu data at this point. But maybe in the future they also make it available. But right now for GPS and Galileo, it's there. It works very well. Okay, so I have some information on the one side, which is more about how you set up your own station. I don't want to go into detail, but if you have the time series for a long period of time, and you're looking at the interpretation, then you have to know a little bit what could be causing any change in that. For that, on this one, this is a station in Malaysia. The scale is quite big, the change. This is a centimeter, so you don't see too much detail in that direction. Why I did that? Because we had a big earthquake and it changed a lot of the position. So if I would take the scale too small, I could not fit here because I want to keep the same scale. But here you see in the horizontal what changed over many years. You see first the linear phase again, then you have the 9.2 earthquake, change the position, then we even have the 8.6, early 2005, all at Sumatra. And you see this pattern, non-linear pattern. And there was another earthquake, 2007, affect Malaysia, and also a little bit the south of Thailand. And then 2012, we had another one. You have to know these earthquake events, otherwise you don't know why you see this sudden change in the position. You know? And if you look at the, and this is the absolute position again. And the change, of course, is north-south direction, east-west. And then again, this is the vertical. But there's an issue here. You know, those two red circles, they change the equipment. And they put this antenna on a higher pillar, which should be perfectly above. But if you look at this, this is a discontinuity. There was no earthquake happening in 2007. Just the height they measure or they give in their own files is the wrong one. This part, red dot, should have continued somewhere around down here. So we had to correct for that before we can properly study and use this. So it would be wrong to just use the raw or unfiltered series like this and do your interpretation, because there are still problems in there. I will show you how to get them out. Okay, the processing steps. Just very quickly, get data, get additional projects to process the data, which can be on the satellites themselves, which broadcast the data. Set up your processing, mostly has to do, have the name, a priori position, what kind of antenna was used by the station, how high the antenna was above the reference position. And then you compute daily coordinate solutions, we call them. So the position in X, Y, Z, which I told you about. Then you can combine them in weekly solution to reduce the noise level. It also looks better on the long-term GPS. This step actually we don't have to do nowadays anymore, but it has to ensure that you're in the proper global reference frame with your position. And then this is where the nicer part comes in, is that you can estimate for every point, of course, the velocity or the position change. And you can also calculate the reference position at a certain period of time. There are many ways to do that. You can do some of it in even in Excel. Some of software packages give you extra routines or apps or applications or small applications. We can do this for you. Yeah, this is very technical, but this is a little bit a state-of-the-art setup you need. Many of those things you just have to tell the software what to use. So actually, we calculate 30-second data, or we log every 30 seconds, but for 24 hours, we actually go down, we decimate at 5 minutes. We don't need even that 30 seconds. But actually, the 30 seconds we need, it's again a little bit of average, not exactly. So yeah, you have to tell something about the troposphere to the system to get your position, and of course you have to know what reference. But this is things you just have to set up. So this way. Then if you have data, this was for Malaysia. They have a lot of stations. They have 180 stations, and I'm not interested to process 180 stations for 27 years because it's possible, but it takes a long time. So I want to make a selection. This was about vertical line motion, relative sea level rise. So we looked for continuous GPS stations close to tide gauges, because the tide gauges, they don't have GPS. So we want to use the core station, the Gnss station, to estimate the vertical line motion and see how well it fit the vertical line motion of the tide gauge. Also in the past, there were stations like we did for Phuket, which had valuable data, but they stopped working. They were replaced by another station, which started working later. So then the new and the old station, we try to get them close together so we can combine the position time series. These are just some practical things, you know. You can also put some station in the middle of the land, far away from the coast, or in areas where there's no people or no cities. It would be a nice reference. They should not have land subsidence because it's just jungle there. So you can also do that. Okay, and yeah, the idea was, of course, to get as many of the vertical land motion information along the coastal region of Malaysia. And we did that. And at the end, I tried to get a nice distribution both for Peninsular and East Malaysia. So this is for peninsular Malaysia. Of course, this is Getty, and Arau is here, and actually very close around here, I think is Oakland. So you're quite close to the station because Azrul is living here, my colleague, and it's only 70 kilometers from his house to Hajar, so he can come by car. So all those little faint, you will probably see it better when I give the presentation. These are all the stations they have, but I only use the one which are the more yellow, clear dots. So they're all around the coast, and a couple inside. And the red ones are actually the locations of the tide gauges from the Malay on the peninsula. So I came up with a final selection. So that's just to show you that when you have all the data you can get from other people, you might not have to process all the data because you only have to process the data which is interesting for your. If you're only interested in this area, then you would not process all the data from around Bangkok. You know, you might include some station near Phuket to have a reference on the other side of the sea. But yeah, so that's a selection you do. And some old news station was here. I could connect also here, so I could make this long time series. I will show you. And also IGS. IGS is a service which has stations all around the world, but not that many yet in Southeast Asia. But there's one station in Singapore, which actually a long time was installed also by Delft. When in the time when the Singapore or the other countries didn't have that much budgets. So actually a long time ago, the university got the receiver. Nowadays they can manage themselves. Singapore is, yeah, also university get quite good funding. If you measure something, then you should already have an idea of what you can measure or about the magnitude, just to give you some confidence. Like I told you before, the tectonic plates, they cannot move vertically, they can only deform in the plate boundary zone. Uplift, nothing is going to move up unless the nature is doing it, because it's just too hard to push up a mountain by yourself. Again, and I already stressed a couple times, human-induced land subsidence due to groundwater destruction in populated areas with monuments on sediment layers. So you have this city or this area, big sediment layer, so you cannot put your station on bedrock, so you have it somewhere on the sand, 5 meter deep, 10 meter deep foundation, but still the land can subside below the 10 meter. If the aquifer where the water is at 20 meter or 50 meter, you will still measure that number. So for this area, I estimated before, and I'm not cheating. I'm from Phuket. I had some idea. I estimate I'm never going to get the rates of PLM if I verify my own results. It should not be lower than -10. This was not Bangkok was higher actually, some areas, but there is no big city. Kuala Lumpur is away from the coast, so it's a different setting. And uplift, I put it +1. I don't expect any tectonics in that area where. Then you know already when you process your own data, you get an estimate and you come up with 50, you know something is wrong. You'll not get 50. So it's good to, and very important for Malaysia, when we apply for the, not apply, it was a project for the government, but when we said already that we had experience from South Thailand, and Phuket is not that far from Langkawi Island, so we said already, we told already that we noticed some things. We like to check if the Malaysian data show the same. That was actually nice also for, yeah, they're quite interested because it's we had some ideas already before going in by working before or working in other areas nearby. Okay, this is a lot of the processing result if you're interested in that, but I processed for 53 stations on for this whole period of almost, what is it, 8 up to 27 years. Unfortunately, they had some problem with the heights and types of the antennas. They're not doing a good job. When they change the antennas to the years, they're not always wrote down. And now we ask them the information, they don't know anymore because the people retired. So I have to correct myself, which is possible, but it took me quite some work. But that's things you ready. The data is never perfect. If the data is perfect, it's so easy. I think it's for you to say it. Whatever data is not perfect. Sometimes there's issues with the data, and either you can understand and you can correct, or you cannot understand and then but you cannot just delete bad data. That's bad science, you know. Some people just don't show the bad data, but you have to try it. If you're not explain it's an outlier, you throw it out. And some of the data also had bad quality because something happened, the receiver got damaged, I don't know what. So, but you only find out when you process 27 years, that 4 years we could not use. And then they replace the receiver at some point. They should have checked, of course, in those 4 years, but sometimes it did not happen. The light was on, the data was coming in, but the quality was not good. Also, they had a big gap for 6 months because the virus hit the Windows server and they destroyed. They didn't have the backup, so they lose 6 months of the network, which is unfortunate, but they could not recover. That's also a problem because you get the gap, and then they change. I'll show you in the next one. And they also had some problem with they changed the station name, but it's the same station because this station is part of the global network, and it maybe give problem with their processing. So at some point they just rename it, but it's the same station. So they're so in one station they move by 25 kilometers with the same name. Normally you don't. If you move, you have to give a new name, you know, or you put a 2 in the back. And the GPS station have four digits. So you would put bear 2, you know, to show that it's the new monument. So I only found out when I processed. In the beginning, my linear regression just explodes because it's only expecting changes of millimeters over a period, and not in one day 25 kilometers. That's way behind the a priori standard deviation. So that then you have to correct that. At that moment, I got angry because they didn't tell me, but at the end, okay, all good, we're happy. This is nice also, technically, if you work on GPS position time series, if you estimate a change in motion, millimeter per year, you always have to also have a good standard deviation or error estimate. Some of the statistics errors which come out of the linear regression, they are simply too low because some of the error sources are not calculated into the standard deviations of the GPS processing. So you get this, if you get like the vertical motion is like 5 millimeter per year plus minus 0.001 millimeter per year, it's not possible. But the statistics say it's correct, but it's not because the statistic is using the standard deviation and then the number of samples, you have that too, so you reduce, but it's not correct. Plus there are some non-systematic jumps in the time series. So long time ago, I tried to come up with a very easy way to estimate, which has to do with the noise level and the time period of the observation to get an idea about the maximal linear tilt of my trend line to get an upper margin. And that one actually works quite well. So it's just explained here, so you have a realistic error estimate for whatever you estimate. Now I call this the position time series. I will show you an example on the next slide. When they come out of the processing, I call them unfiltered. There are still errors in there because the antenna height change at some point, or they put a new antenna and it's not documented. So I see jumps in the position which has nothing to do with your physics or subsidence. It's just an error. So we have to figure them out by self. You can write software for that, but you just look with your eyes and identify and look at what week it happened, so you know you have to do something there. And then the end product, we call it the filtered GPS time series. That's the pure, correct scientific data you end up with, which you can use for your interpretation. But you have to get there. And the processing you can do automatic, but sometimes here people make mistakes, and then it affects the results. If those vertical offsets you see, because something changed to the equipment, are not documented, or still after you make a correction they give you, it's not correct, you have to estimate yourself. Because you don't want to have a big jump in the height when nothing at all happened in that period. So that again is I did that manually for all those stations. It's quite some work, but at the end I end up with something nice. I will show you some examples. And also for a couple stations, old, discontinued, a new one I combined so I could have a longer time series too. And the final run also we include the seasonal changes in the vertical. These are those sinus or cosinus modes, which are not that important for our study, but you have to know, which is not complicated. The software for that you can find online. Now, this is just to show you the unfiltered time series, the same one you saw a bit earlier. But now let's, on the right side, we call it the detrended version. That means now we just plot the differences with respect to the blue line. So the blue line is the trend we estimate, and this is a zoom in with respect to, so that line is now horizontal, you know. So we look with respect to this line, because then we can see much more the changes. Now here it looks perfect, you know, but if you zoom in, you actually see more the noise, which is normal with zooming in. But if you look at the vertical, you see that there's two issues here. This jump should not be there. And also here they change the antenna, also here there's a jump. How to jump? Technically, I did that. The software can estimate for you jumps. It can be also if you look at coral growth. But the problem is if you have many jumps and we have a very long period of time, then sometimes the estimation of many jumps together with the trend is decreasing the reliability of your end result. So you can do software automatically, but you can also do it manually. With GPS, we can do manually if we have a station nearby, which in the same period we see something happen because they changed the antenna here, but this station they not touch. Then we can check how the baseline between those stations change with the old antenna or the new one, and we can estimate very precisely up to the millimeter level that change and correct for that. That's explained here. I will give you, for those interested in detail. An example of that is here. And this actually is another example. I showed you the previous one, but here you see nothing happens to the station, so it should not have. Okay, this one I didn't show you before. Before we put the permanent station, we put the tripod next to the house to measure for a couple of days. But the tripod is a measurement for 3 days. We put the tripod on there. It's difficult to see here and here, but it's next to the house. It's blocking the horizon of the visibility. So the data was not that good. So this is not a change, but it's, and the second one, I already put the antenna on top of just above the roof. And that was already better. That's this one. But now we put the permanent station and you see nothing changed in between those two stations. But if you look at in Malaysia, this is the one station with respect to another station. You see that nothing, it goes like this, and then suddenly there was a period where the station was not working anymore, and they upgrade, and they start again, and suddenly you see this. You see, this is not correct. The position changed in between the station because they put the antenna a bit higher or lower, and we want to filter this out. So for the Malaysian work, it was quite some work. I think at the end, I did like 60 of them jumps. I had to estimate manually, but now you see the result. This was before, okay, that's not so nice, unfiltered. This is, and this one is after. Okay. So now you suddenly see here that it looks much better. We don't have this discontinuity anymore. See, this one is gone. Also this station, that was wrong due to equipment change. Here you see, now we get a nice thing. It's not nice still because you still see go up and go down, but that's due to the tectonics. Due to the earthquake. So you see here we go from unfiltered GPS positions to filtered ones. And then we can do the same for many of the stations. Yeah, no, actually near the end. So and then if you look now, do you see similar patterns in those 4 stations? This is Kuala Terengganu, this is Getty, this is very close to the Thai border, you know, on the eastern one. This is Langkawi Island. This is on the western side, just below the Thailand border. UMK is a little bit south, but these are stations which are relatively close to Thailand. But do you see similarities? So those 4 stations, if there's something going on, tectonics, this is the vertical, right? Vertical direction. The 4 stations should show something similar. Now we have to make interactive. So do you see similarity? Do you see the same pattern? And then one thing you see that this station only start after just at the end of 2004. These were new stations, and this station already started operating in 1999. So of course, if you cut this off, you can see that actually this pattern from here, oh, it's difficult with the point. This one going down here, this one going down here, and this one going down. This is just after the earthquake. Okay, it's here. You see that there's this pattern. It starts up and then slowly it starts to go down. And before the earthquake, it seems that this area was going up, and this area was also still going up to here. I will show you in the next slide. So actually, we see these different vertical motion periods before and after this big earthquake at the end of 2004.
But it's not so clear like Phuket. Huh?
No.
It's just because Phuket is sharply.
Okay. And why is it not that clear?
Maybe it's.
I think I already mentioned. You're close to the.
It's close to the.
It's closer to the earthquake epicenter. Phuket was much more affected. The horizontal was 25 centimeters. This station was only like 10 centimeters. So that's a factor 2 already. So also in the vertical, we see it. We see the further you go away from the epicenter, but you do see the change also here. But it's like a scaled one. I have one slide coming up which shows you on the right side to Phuket, and the other one is Kuala Terengganu, which is on the east coast, you know, I think a couple 100 kilometers below Thailand, you know, but in the Gulf of Thailand. But that one is coming up. Oh yeah, it's here. Okay, so this is the one. You can go directly to the next one, but this one is the one I still look. Also, I saw some weekly solution because the receiver was not working well. I throw some out, you know. So we call this outliers, you know, outlier detection. You have it too if you do sampling. And then the bars here are the number of vertical position jumps due to equipment change. I had to filter out. So I just plot them as a bar because people look at your results. They have to know where you did the correction at one point in time, you know. So you see that if you have a station for 15, 20 years, for sure, at some point, they had to change the antenna because it got hit by lightning, or they got the new equipment and they want to change, although the antenna can work for 20 years or more. If you don't have to, never change the antenna. But there are a couple, but the less of those jumps, the better, because you don't want your data being influenced by a change of equipment, you know? But it's not always possible. Okay, then the next one is the same, but here already we start fit the trends. And we also fit the seasonal, which is the little green line, which is all vertical. But actually here, and when you get the printout, you can see for this station, it's non-linear. But we're looking at relative sea level rise, so we just ignore over the long term, we ignore those couple first years, and we fit the linear trend to the later period, you know, because the linear trend has advantage. You can compare the rates. If you fit a non-linear trend, that's nice, but it's not so easy to compare millimeter per year. If it's and actually for the stations which had data before the big earthquake, we have a linear trend until before the earthquake, and we have a linear trend after, but ignoring the first couple of years, just to get a more. We're going to compare this. In the paper, we compare this with the estimate from the tide gauge. That's why we have. The tide gauge has much more data, but it's much more noisier. The GPS, the vertical line motion, is more accurate. But if you include data which has this non-linear, it will affect the trend much quicker. So to do that. And actually, you see uplift before, you agree with me. And you already see the same for Phuket. So we see the same in Malaysia. So it's not the error of the processing because it's totally different data and even different. We already saw it with the different software also, but yeah. But if we didn't have all those years, we would not see the change, you know. So then, of course, you want to plot it. I split the stations we had data before. Again, it will look better when the plot is. If you look in the file, it's clear. So we distinguish between two periods, the beginning of the GPS till the end of 2004, 2005 till now, because it's two different periods. because of the big earthquake at the end of 2004. And it's difficult to see. Yeah. So you see the arrows are small. If you look, it's hard to see all of you, but in general, you can see that the green arrow before the earthquake is smaller up, and the one after the earthquake is downwards, or at least less upwards. So it's a change. But there's a couple of stations here which have very big rates. You know, this is the one station is 3.3, and the other one is, you see my eye, 5 millimeter per year. What do you think this come from? What are we measuring here? Because the rate is too big compared to the other ones. They're not outliers, so the measurement is not wrong, because the standard deviation in the error ellipse is quite small. So the GPS station, the GNS station is really moving down. Why is it moving down?
NTU.
Yeah, it's 4 and 5 millimeter. That can never be tectonic subsidence.
I think
Yeah.
NTU is in Singapore, right?
No, huh?
NTU is in Singapore.
Yeah, no one is nearby. No, this is Kupi, I think, here. Kukup, I think it's near Singapore. But Dr. Ko already said these are GNS station on sediment, and there is groundwater extraction. So they're measuring the rates are due to the land subsidence, human-induced land subsidence. The other ones, they are much smaller because either there is no land subsidence or the points are better. Kuau, we know, it's a geodesic point, it's on a rock. And that one actually is the one which shows the most beautiful signal, because it's not polluted by local or regional land subsidence, you know, to the people. Okay, now this Dr. Prakrit said before, now we compare Phuket with the station at Kuala Terengganu, and you see the same pattern, but you see horizontally here, the jump here was only, I don't know, less than 10 centimeter. In Phuket, horizontal was 25 centimeter. So it scales. So you see the same, but if you could scale this one, if you unify this one, you know, and then you could try to match it, not perfectly, but it would go. And here you see Phuket, and you see the subsidence in Phuket was much more stronger, but also here you see it, you can see the signal actually in Phuket was higher. And the uplift was also a little bit higher, but the uplift is more smooth for the whole plate, you know. So the signal was a couple of millimeters, but you see the subsidence due to the earthquake is much bigger in the south of Thailand, near Phuket. It's not only Phuket, it's also Ranong, and there will be a maximum somewhere. And it's also still going to be Songkhla, Hajat too, but less again, you know, and similar to the one you see in Malaysia. But for sure, if we had the GNS data from Songkhla or from Hajai for a long period of time, I'm sure we see the same pattern, but smaller than Phuket, but still visible. But without Phuket, we maybe would have never noticed. We just think it's a noise, and we fit my trend. But the Phuket was so clear that we can. So actually, we use Phuket to validate also and to check we see the same. So that almost brings me, yeah, to the end. So from the Phuket Island, and maybe that's interesting for proposals. So what I want you to take away, that means you can take your food away, but if you take away this, then if you forget all the things, but you still remember this, then you still have some, get some knowledge there, you know. So we see that the vertical land motion clearly had some tectonic uplift before 2004. That might have been going on already for 100, 200 years, and that Phuket Island was going up because there was no big earthquake. The biggest earthquake was 200-300 years ago, I think, in Sumatra, in the same area. We don't know exactly because we didn't have satellites. We only have the old records for the colony or for the Dutch or for some people generation living. They said in Thailand also, they said the gypsy living some island, they say, yeah, like 300 years ago, their great-great-grandfather had the same, and they always tell to run to the hill when the earthquake or the water go down, and they still remember, you know. But so we don't know, but then, yeah, we're lucky or unlucky, of course, for the many people who were affected or lost their life. That we see that it started in a downward motion, which is of course decreasing. But still now at the last years it's flat, but before it was going. So we're still in this post-seismic phase, you know, to look at. So that's something you have to know. We call it tectonic uplift, tectonic subsidence. Tide gauges, they show a linear relative sea level rise. I will show you. Yeah, I will show you one result coming after that for Malaysia. This was for Phuket until the end of 2004, and then we suddenly see that the relative sea level rise in Phuket was increasing much quicker in a non-linear pattern due to this vertical land motion. Satellite altimetry is not affected by anything happening to the land. It's just the absolute measurement of the sea level. So that one is just the one due to the present climate change and the regional sea level rise, which is a little bit different. And the global average is so many millimeters per year. Some areas are a bit higher, some areas are a bit lower. Has to do with also the redistribution of the water, and some currents changing also because of the weather, storm patterns. So, but on average, and I also showed you in the previous talk that we see the same pattern at quite some other tide gauge stations in the south of Thailand. They were all on the Andaman Sea, but I'm sure if you would look at the data of the Gulf of Thailand, Koh Samui is too far, but we go more to the south. This area, area between Songkla and let's say where you take the ferry to Koh Samui, on the big city there. Yeah, Suratani. In that stretch, we probably would see a similar signal, be it a bit smaller because it's more far away from Indonesia or Sumatra, where the earthquake happened. Okay, combining. So to do the validation, if you just subtract vertical land motion, it's the way you want to go. It just means that you have two independent ways to end up with relative sea level rise, either directly from a tide gauge or using the satellite altimetry and the vertical land motion from GPS. They fit very well for Phuket. They were almost a perfect fit, and we not manipulate the data or create this outlier. So we were quite happy with that. Malaysia actually was not that good because there's some issues with some of the tide gauges. And then of course we asked when we talked to the Malaysians, are these results important for relative sea level rise also on peninsular Malaysia? Should be, because the tectonics do not respect the national borders, so they should also be affecting there. So and then almost end, just to show you an example for that. This is the VLM for this station, Kuala Terengganu, which is at the station on the Gulf of Thailand, a couple hundred kilometers away from the Thai border, which is located on bedrock and already was measured in 1994. This first European project, only one black dot, but we had a dot here, a dot here. They're not so visible, but they're here and here and here. That's still extra data, you know, we can use. Now you see the same pattern as for, but it's a bit, the scale is different, right? It's smaller than Phuket, but the scale here is 20. I think the scale here is for Phuket we use a bigger one. So, but yeah, it has the same, but it's smaller. This is the tide gauge, has a different name for that period. It's a bit difficult to see actually, and the scale, the data starts in 1982. This is 2004. But also here we estimate two different trends. So we do one trend here before the earthquake and one trend here starting a couple days after. And we compare that with the trend of the, this is the, I'm wrong, this is the, forgive me, this is the satellite altimetry. So it's one trend from space. So it gives you an estimate, so many millimeters per year. Actually, it's summarized here. And this is the tide gauge. The tide gauge also we split because we know that the vertical land motion is not the same pattern. So we split. It's more difficult to see in the tide gauge because the data is more noisy, but actually for the Phuket one, we can see it's very clear. Here we can also see it, but it's a little bit more difficult. And here we did a linear trend to be able to compare. So this is VLM, this is satellite altimetry, and this is relative sea level rise directly from a tide gauge. Now, if you look in the table, which you cannot see, so you have to trust me, I have the numbers here. You know, when you get and then we have the number of tide gauges. The nearby GNS station, how many kilometers? Actually, preferably should be 0. You like to have your GNS directly on the tide gauge, so you're sure it's measuring the same vertical line motion. And we have estimates for the absolute sea level rise, which are all between 3 and 4 something millimeter per year. Then we have the vertical line motion. For the stations, we had data before 1999. Before 2004, we can split the trend before and after the earthquake, so uplift and downlift. Then we have the tide gauge data, which they have a long database, which are given here, also split before the earthquake and after. And then we do the trick to calculate the relative sea level rise by subtracting the verticalized motion from GNSS, from satellite altimetry, and we compare the numbers. And actually, after the earthquake, our number agreed within 1 millimeter per year, which is quite nice. And before the earthquake, also the linear estimates, they also agree within 1 millimeter per year. So actually, we do the validation and they agree quite well. So it's the purple has to agree. The purple here has to agree with the purple here, and the blue here has to agree with the blue here. There's also a couple outliers, but that's because of local subsidence. I show you those stations. The station is subsiding. The GNS station is subsiding, but the tide gauge is maybe on a different foundation or a different pier. It's not seeing the same, then they don't match. That's why you like to have if you look tide gauge, you should have the GPS or GNSS at every tide gauge. Well, we do that now at Kota Noi and Phuket, but the Thai agency, I think they're still in the process of getting the budget. The DMR wants to do it, to install them, you know. We wish we already had them. The Malay also, we told them why you should also put them closer, you know. They have, so that worked very with validation for the sea level rise was quite nice. So when you put the printout, you can look and you see that those numbers agree very well. And also that they overlap with the realistic error estimate. The error estimate is about 95% confidence. So that's the typical number we give for that. It's around 0.3 millimeter per year. So that's what we say that how accurate we can estimate sea level, because there's always some variation. I think, yeah, that was the last slide for the talk. So I made it before lunch. So
Yeah, okay.
I hope you not fall asleep, but I give you the printout that you can use all three.
Maybe
And if you have any questions,
copy. Yeah, and copy. Maybe we can discuss on during lunch.
yeah, we can. Yeah,
ใครจะถามอะไรก่อนไหม อยากถามเลยไหมก็เลยนะ
Anybody else?
มีอะไรจะถามไหมเด็ก
Yeah. It's Windows 7. There's no virus anymore on Windows 7.
You know, now it's tomorrow later. Tomorrow later, maybe.
ๆแค่นี้ไหนครับ
Tomorrow later.
แอนจะฟังกันไหมกับพี่กิตด้วยเราค่อยเปิด
Yeah, oh, thank you. Yeah. And
พรุ่งนี้ไปรับเขาไปเขารู้เรื่องของ
so it'd be number 1 is the first one, number 2 is the other. I don't have to tell her. That is the presentation part. Okay. And
So thank you so much for your presentation.
yeah, I hope
I think not that today. We will contact you and I think when we propose the program.
yeah.
Sooner or later.
This is just a background and we have some publication also already.